This huge dish is at one of the world's great observatories, not perched high up on top of a mountain, but just over 20 miles from Manchester. It's the 250-foot radio telescope at Jodrell Bank. You can't look through it, as you can through an optical telescope, and it doesn't matter how thick the clouds are, because it doesn't see at all. It's picking up invisible radiations. This year marks its 30th anniversary. It first caught the public imagination in October 1957, when the Russians started the space age by launching their first artificial satellite, Sputnik 1. And outside the Soviet Union, this was the only instrument in the world capable of tracking it. Incidentally, the telescope weighs something like 2,000 tons, and that's about the same weight as the Saturn V rocket which launched men toward the moon. So no wonder the rocket lifted off slowly. I suppose everybody's heard about radio astronomy, but I wonder if everyone understands just what it implies. Well, light is a wave motion, and the color of the light depends upon the wavelength. The red light is longer in wavelength than orange, orange longer than blue, and so on, down to violet. Now, if the wavelength of the radiation is longer than that of red light, we can't see it, but we can detect it as infrared. And there's an easy way to show that. Switch on an electric fire, and you will feel the heat as infrared well before the bars become hot enough to glow in visible light. Now, beyond infrared, we come first of all to microwaves and then to radio waves. And it's the function of a radio telescope to collect these radio waves which come from space. They are caught by the big dish, and they're sent up to the aerial, where they're brought to focus in basically just the same way as visible light, because a visible picture is not produced. The waves are sent down to recording equipment, and the usual end product is a trace on a graph, which may not look very imposing, but is immensely informative. Radio astronomy didn't begin in earnest until after the end of the last war, although in fact radio waves from the Milky Way were picked up as early as 1931. But you know, little more than 30 years ago, the idea of building a dish of this size would have seemed absolutely fantastic. And but for the courage and energy of one man, Professor Sir Bernard Lovell, it wouldn't have happened, and radio astronomy wouldn't be where it is today.
The experiment I originally intended to carry out has never been done. When I came here, we immediately discovered and ran into this whole new field of what became known some years later as radio astronomy. And the large telescope, which you see here, really was developed from those original ideas. I mean, first of all, in 1947-48, we built a big wire paraboloid, 280 feet in diameter, which could only look towards the zenith. And then at last I managed to find an engineer, Sir Charles Husband, who said it was possible to build a device of that size which was steerable. And after many traumatic experiences, this developed into the instrument which we began using at Jodrell Bank almost exactly 30 years ago.
I think it's fair to say the Sputnik came along at a rather good time for you and for Jodrell Bank.
Well, it did indeed. I think a few days before it was launched, I said to one of my colleagues, we needed a miracle to save us because we were in such disfavor and in so much debt. And that miracle did come on October the 4th, 1957, from behind the Iron Curtain.
When it was built, it was really an act of vision because there wasn't much idea of what astronomy would actually be doing. These days, the astronomy we're doing is practically unrecognizable. It's so exciting to have seen many new things, new concepts during those 30 years. At the beginning of that time, we didn't know about pulsars, we didn't know about quasars, we certainly didn't know about megamasers. And those are things which are really at the heart of modern astronomy.
When you first came into radio astronomy, had you any idea of the way in which it would develop?
No idea at all, really. We were picking up radio waves from the sky and we didn't know where they came from. We didn't realize that we would become astronomers, in fact. We didn't call ourselves astronomers at the beginning. And it developed into one of the most important branches of astronomy.
There are still some people who believe that radio astronomy and optical astronomy are two entirely different subjects, not connected in any way.
Oh, of course they do, but it's quite wrong. There's a wide spectrum from radio all the way through optical, X-ray, gamma rays and so forth, and we play our part in it. After all, radio astronomers go and use optical telescopes as well. If we've got an object which is like the Crab Nebula or the Crab Pulsar, which emit over the whole spectrum, we may work on it from its radio waves here, but we then go and use optical telescopes to look at the other part of the spectrum. In the same way, optical astronomers come here and use radio telescopes. It's complementary.
Now we're in one of the observation rooms. Among the many objects studied here at Jodrell Bank are pulsars. And a pulsar is the result of a supernova outburst. A supernova occurs when a very massive star, more than 8 times as massive as the Sun, collapses. There's an implosion, followed by an explosion and a shock wave, and the star sends most of its material away into space. And the end product is a tiny, super-dense object made up of neutrons. And you could pack 1,000 million tons of neutron star material into a matchbox. Now, this neutron star is spinning round very quickly, and as it does so, it sends out radio waves. And these radio waves come out in beams from the star's magnetic poles. And if we pass through one of these beams, as the star spins, we get a pulse of radiation, hence the term pulsar. And the effect is rather like that of a rotating lighthouse beam, only here, of course, we're dealing with radio radiation and not visible light. Plenty of pulsars are known. There's one inside the Crab Nebula, and we know about that one. It was formed by a supernova outburst seen way back in the year 1054. But there are also some pulsars which spin round very much more quickly, and these are known as millisecond pulsars. Until recently, only 3 were known, all discovered at the Arecibo Radio Astronomy Observatory in Puerto Rico. But here at Jodrell Bank, Dr. Andrew Lyne has been carefully searching for others, and recently he found a 4th. What is so unusual about this particular millisecond pulsar?
Well, apart from the fact that it's in a globular cluster, which tells us how these millisecond pulsars were likely to be formed, it's also lying at a considerable height off the galactic plane. This will give us important information about the interstellar space between the pulsar and the Earth.
Why is the inside of a globular cluster such a good place to look for millisecond pulsars?
Well, a globular cluster is a gravitationally bound swarm of stars with a very dense population in the center. The stars are all buzzing backwards and forwards. It's a sort of stellar cauldron where there are plenty of interactions between the stars and a fair chance that an old pulsar will be caught up by another star and spun up to a very short period.
We've been talking about stellar deaths. Now what about stellar births? Look at this picture. I'm sure you'll recognize it. It is the famous Orion Nebula that you can see with the naked eye below the 3 stars of the Hunter's Belt. It's a tremendous mass of dust and gas, more than 1,000 light years away. And inside this, we believe that fresh stars are being born. Obviously, we can't see them deep inside the Orion Nebula because there's too much dust in the way. But we can detect them by their infrared radiation, which of course is not blocked out by the dust. And we know that inside this there's at least one tremendous star, which we call BN, which you can never actually see and never will see, but we can detect its infrared. But there are other things too inside the Orion Nebula and elsewhere, and these are called masers. So what is a maser? Maser stands for microwave amplification by the stimulated emission of radiation. And a cosmic maser works rather like this. We begin with what we call an OH molecule. Now, O stands for oxygen, H stands for hydrogen, and of course water is made up of hydrogen and oxygen, so an OH molecule is made up of the same kind of materials. When these molecules are bombarded by infrared radiation, there's a very interesting effect. Their spin is increased, and therefore they have more energy than they would otherwise have. But this doesn't last. They cascade back to their ground state, so to speak, but they're not quite. There's a certain excess left there, and this is cumulative. And when you have enough OH molecules being affected in this way, the end product is a tremendous emission of microwave radiation, bearing in mind that, as we've seen, microwaves are longer than visible light but shorter than radio waves. And that is what we call a cosmic maser. But we also have things called cosmic megamasers. And one man at Jodrell Bank who's been paying very close attention to these is Dr. Jim Cohen.
Well, megamasers are a new type of maser which are millions of times more powerful than those we know about in our own galaxy. It's as if you could take the energy output from 1,000 stars like our Sun, a total energy output, and convert it just to a single narrow microwave signal.
Where do you look for them?
Well, the signals are produced by these hydroxyl molecules which are in molecular clouds, clouds of gas and dust in the centers of certain types of active galaxy. The nature of these galaxies only became apparent when the results came in from the IRAS satellite, and it turned out that the megamaser signals were being produced by galaxies which were extremely luminous infrared emitters. They produced most of their radiation as infrared radiation, and this is because the energy source itself is hidden. It's being blocked by these dense clouds of molecules and gas and dust.
What exactly is the energy source of a megamaser? Do we know?
Well, if we knew that, we'd be very happy. There are two basic competing theories, and one is that there is a single very powerful energy source in there, something like the nucleus of a Seyfert galaxy, and then we'd have something that was of a scaled-up version, a simple scaled-up version of the maser situation we have in our own galaxy, where you have a cocoon of gas and dust around one young star. But the alternative people are putting forward another view that we might be dealing with a starburst, and here the idea is that there are millions of stars, all born at essentially the same moment in time in this very confined space in the nucleus of the galaxy.
Well, two ideas. Which do you favour?
Well, the evidence we have is marginally in favour of the idea of one single energy source. The reason for that is that when we look carefully at the spectra, the OH maser spectrum, then what we find is that the emission is telling us that the gas in the centre is moving extremely fast, motions of perhaps 1,000 kilometres per second. And that's the type of motion which you would expect to find in the nucleus of a Seyfert galaxy. But it's not the sort of motion you'd expect to find in the case of a starburst situation.
We've been talking about violently active galaxies. But what about more normal galaxies and the makeup of the universe as a whole? A great deal of work is going on here at Jodrell Bank by, for example, Professor Rod Davies.
Well, one of my big interests with the Mark I is using it to measure the 21 centimetre line from neutral hydrogen in nearby galaxies. In fact, the Mark I is an ideal instrument for that because it's got an angular resolution of about 12 minutes of arc, which enables you to measure the total radiation in neutral hydrogen from nearby galaxies.
Why are you so interested in that?
Largely because it tells you about star formation. We used to measure the hydrogen in our own galaxy, relate it to where the spiral arms were. We looked at M31, the Andromeda galaxy, and then moved out to the more distant galaxies, and it gives us the amount of gas in those galaxies which are available for forming new stars.
What other information does this give you?
Well, one of the great interests in looking at nearby galaxies is to get their total masses, which you can get from the rotation of the galaxies. And that total mass, or the rotation speed, can be used as an indicator of how far the galaxies are away. And this really is the big new advance in hydrogen line studies.
We've been talking about galaxies that are very close to us on the cosmical scale. What about those galaxies which are further away? How far can you go?
Well, we can go out to something like 100 to 200 megaparsecs with the Mark I telescope. That enables us to see hydrogen in those distant galaxies, and I guess the cluster or group of galaxies that we're most interested in is the Virgo cluster. And from our measurements of nearby galaxies, we find that there is a small flow or movement of our galaxy towards that Virgo cluster. This is one of the galaxies that we've used to measure the Virgo-centric flow. It's a galaxy called NGC 289, and it is at a distance from us of about 100 million light years away. You can see the clear-cut spiral arms, and that tells it's an SBC galaxy. Before we started our study, only the central parts of this galaxy were known, the bright parts on the picture. And when we used the Mark I telescope to survey the hydrogen in it, it became clear immediately that the galaxy was much more extensive than the early optical photographs had shown.
What about the microwave background?
The microwave background is something we're very interested in here at Jodrell Bank. It is, in fact, the radiation which is the afterglow of the Big Bang. And what we see with our radio telescopes and special horn systems we use here is the radiation that comes from some 1 million years after the formation of the universe, after the Big Bang occurred. And this information tells us about the structure in the early universe that eventually grows to form the galaxies and the clusters of galaxies around us now.
One radio telescope is all very well. Two, working together, are much better. And here at Jodrell Bank, we also have the Mark II radio telescope.
We are attempting to use the Mark Ia and Mark II telescopes here, linked together as an interferometer, to study fluctuations in the microwave background. You see, the real mystery is, why are there galaxies? Why in the universe are the stars not spread out evenly? Why do we have islands of stars and then a large gap to the next galaxy? What this means is, in the original fireball, there must have been fluctuations. There must have been some regions which were bright and dense, and some regions which were faint and less dense. And in time, the bright regions would then become the galaxies. So we are attempting to measure these fluctuations, and they are proving extremely difficult to detect. We have two experiments that we're following up on a larger angular scale size, 5 degrees. One of these experiments is on Mount Teide, on the island of Tenerife, and the other one is here at Jodrell Bank. And we are now beginning to detect fluctuations. The real surprise is how weak they are. It means there is a real problem in the galaxies coming into existence. And we're beginning to think that the conventional material, we call it baryonic material, that is protons and neutrons, the sort of material that you and I are made out of, cannot be responsible for most of the mass of the universe. And we are beginning to think that most of the mass must be in a form as yet undetected. We refer to this as cold dark matter.
Any idea what it could be?
None whatsoever, I think. Maybe the neutrino. It's been suggested the neutrino may have mass. It's certainly some form of physics that we don't really understand as yet.
Quite apart from the two main telescopes here at Jodrell Bank itself, there are others much further away. Because if you have radio telescopes widely separated, you can combine their results and make them work together so as to produce the results you would have got with a single telescope of that aperture. And this is the principle of what we call the Merlin network, with which Dr. Tom Muxlow is deeply concerned.
Merlin is a collection of telescopes around England, and it's called Merlin because it stands for the multi-element radio-linked interferometer. And that's one telescope here at Jodrell and 6 other telescopes around England, joined to Jodrell by radio links, and their data are brought back to Jodrell along these links, hence the name.
Why do you need more than one telescope?
If we want to make radio images, that's radio photographs, of comparable resolution to that of an optical telescope, then we need a physically large telescope, because radio waves are a much larger wavelength than those of optical light.
As we're dealing with invisible radiations, how do you get pictures?
First of all, most of our theoretical telescope doesn't exist. It's clearly impractical to fill England with telescopes, and therefore we only have a few sampled strips of our telescope. This has the effect of making a very poor, raw image, and we have to improve the quality of this image in a large computer, enhance that image.
What objects are you looking at?
We're looking at exploding galaxies. A small proportion of the population of galaxies, perhaps less than 0.1%, show this activity. And what happens is that the nuclear region of that galaxy explodes. Material is being drawn down into a compact object at that center, and around it a great fireball is created and generates 2 twin opposing beams of relativistic plasma. This plasma is then ejected clear of the galaxy into intergalactic space and actually radiates in the radio bands, and it's this that we detect with our radio telescopes. And we in fact attempt to take radio photographs, detailed radio photographs of these clouds of plasma thrown out from the galaxy. It is, if you like, smoke from the distant explosions in these galaxies.
When you talk about a compact object in the middle, do you mean a black hole?
Could be. In a number of galaxies, it is clear that there is a great deal of mass in a very small region of space. And it seems somewhat contrived to try and think of ways to prevent that being a black hole.
What about quasars?
As we go out further into the universe, we find more and more active galaxies, and quasars are one form of active galaxy, an extreme form, and here the nucleus itself is extremely bright, certainly in the optical, and dominates the overall image. And at very great distance, too far to see ordinary galaxies, the quasars are the only things that we can see. But it's interesting to see that, in fact, the radio structures that we get from even distant quasars are very similar in type to those seen around rather nearby galaxies like Virgo, although certainly more powerful, the quasars, more luminous. And I've got an image here of a distant quasar. We call it 3C179, but here you can see there's a central core and a one-sided jet and two lobes on either side. And here, this quasar is at very great distance, in fact, some 10 billion light years away. And the overall structure is almost 500,000 light years across. Remember, of course, the Earth has only been in existence some 4.5 to 5 billion years. So when the Earth was just forming, the radio waves were already half their way across the universe to us. So it's an image of a very distant and early object.
What would you say is the main significance of the work you're doing with Merlin?
Taking very detailed photographs provides the basic framework or database from which theoreticians can come and try and interpret physics. And that's what we're doing here. We are providing high-quality images on which that work will be based.
Every research astronomer has to begin sometime, often when young, and the role of education is all important. And this is something which is certainly not neglected at Jodrell Bank. A major science centre has been established, which is open to the public at stated times, and there's also a planetarium where regular displays are given. The whole centre has been considerably enlarged of late, and new additions are planned.
Years ago, people used to flock here to see what the telescopes were doing in the space age, you know, the moonshots and those. But we soon realized that in providing for those people, we had a wonderful opportunity to present astronomy much more generally. So this is an exhibition not just of radio astronomy, but astronomy in general. Now, having done that, we then realized we had a wonderful opportunity for education. Not just to show the public what we're doing, but to show school children what we're doing and make science fun. So we're developing the exhibition now with a lot of interactive exhibits which children actually take part in. They come and they get their hands on things and they actually do things, and for many of them it's their first introduction to science. So we think it's pretty important to put on a show that will appeal to school children. There are lots of things to do here, and I think that's an important aspect of our exhibition. You can steer a model radio telescope, just like steering the big one. You can play with parabolic reflectors, just like the big parabola. You do this with sound. You go outside here, and you shout into one paraboloid, and you can hear it very well at the focus of the other one. That's great fun. The idea is to get people involved in science and to enjoy it.
So, Jodrell Bank is 30 years old, and what better excuse for a celebration? Preparations are going on apace. Over 400 people are coming, including, I'm glad to say, many of those who have worked at Jodrell Bank over the years. Everything's being spruced up. There's a very party-like atmosphere here. And, do you know, they're even painting the dish. And it wasn't only a party to celebrate the 30th anniversary. There was a renaming ceremony. The telescope has always been called just the 250 foot, but it really ought to have a name. And it was agreed by everyone, all over the world, that it should be named in honor of its founder, Sir Bernard Lovell. So from now on, the Mark I 250 foot radio telescope is to be known as the Lovell Telescope.
It's a very happy moment, and one that could not have been foreseen 30 years ago. But now I think one is confident that the telescope will survive for many more years and will do marvelous work in the future.
Bernard, congratulations and thank you.